I want to look where nobody has looked before.
The size.
Nothing has been built on its scale before.
It's so big and it's so complex.
Boldly go where physicists haven't had a chance to go before.
Hi, I'm Alison, a PhD student working on the CMS experiment here at CERN. I'm going to take you for a journey into my world, the world of particle physics. Follow me.
What I'm doing is really going for the truth, for the most basic fundamental truth.
To have a chance to see something that nobody has even thought of seeing.
To further man's knowledge of the basic structure of matter.
We know the world is not just what our eyes can see. My camera may not be able to see the skiers on the mountains, but with a sufficiently powerful zoom, I could see the traces that the skier leaves in the snow. Particle detectors can be thought of as a giant digital camera that records traces of subatomic particles. But first, let's take a step back. Man has always tried to understand what our world is made from. One way of finding out what something is made of is by taking it apart and analysing the pieces. And then again, taking apart those pieces into smaller pieces, further and further, until we reach the scale of the atom, around 100 million times smaller than that of a grain of sand. This is about the smallest thing that we can see with the most powerful microscopes. But we want to go further, much further. For that, we need a particle accelerator. Particle accelerators use subatomic particles, such as protons or electrons, as projectiles, and make them travel near the speed of light before smashing them into one another. Using this technique, we have discovered that in fact our world, stones, air, even us, are all made from just a handful of different types of fundamental particles. As far as we know, the whole universe is made of the same few particle types: electrons, up and down quarks, and electron neutrinos. However, we also find that when we smash particles into each other, we create particles that don't normally exist, and that only last for a short time before transforming into the more familiar and stable electrons, quarks, and neutrinos. The particle creation happens because matter and energy are interchangeable and can transform into each other. Does this ring a bell? Well, it's Einstein's most famous formula, which basically says that you can create mass from pure energy. When we smash particles into one another, we release a lot of energy and can make new particles. And the more energy that's released, the heavier the types of particles that we can create. We now know that in addition to the up and down quarks, there are 4 heavier quarks, known as charm, strange, top, and bottom. There are also 2 heavier versions of the electron, known as muons and taus, with their accompanying neutrinos. The conditions inside our particle accelerator, huge energies in a very confined space, are similar to those that existed around the time of the Big Bang, some 13.7 thousand million years ago. We are effectively trying to make little bangs in our laboratories in order to understand how the universe came to be and why it looks as it does now. So, particles are all around us. Some of them are heavier than others. Some have electric charge, spin, and so on. And the particular combination of all these properties actually defines the particle. Our quest is to understand why certain particles have certain properties. We develop a description of what we already see and try to predict other properties that we can measure experimentally. In fact, We even try to predict the existence of particles that we have not yet seen. Currently, we have a mathematical description, known as the Standard Model, that explains a lot, with unprecedented precision. But we already know it has its limitations. For example, it doesn't explain why there are only 6 types of quarks, and why they each have a different mass. Maybe one day we'll find a model which describes everything in the universe, a sort of theory of everything.
The theory of everything should be able to help us describe the fundamental interactions as they were occurring at the very earliest times of the universe. They should also be able to help us understand how particles interact in the world as we find it today.
Okay, now that you know it all, let's go to the lab and get our hands dirty. At CERN, we are building one of the world's largest particle detectors, the compact muon solenoid.
Over 2,000 scientists, including 400 students from 155 different institutes spread over 37 different countries around the globe, are working on this huge project, which started back in 1990.
It's a large collaboration of people all trying to work together to achieve a common goal.
I've seen people from almost all the continents, and that's the most exciting part.
CMS is one of the large experiments at LHC.
A detector which is being built to test various aspects of our current knowledge of physics.
It's a big magnetic spectrometer. It is the equivalent for particle physics as a medical scanner is to the doctors.
It will be constructed and running from around 2007.
The CMS detector will be over 20 meters long and 15 meters in diameter. It will weigh more than 12,500 tons. That's nearly twice the weight of the Eiffel Tower. The detector will be assembled and tested in the surface hall, and then lowered in segments into a cavern 100 meters underground. This is the cavern where the detector will be. CMS is based around the world's largest superconducting solenoid. It will be housed inside this tube. Its magnetic field will be about 4 Tesla. That's about 100,000 times that of the Earth. But don't let this amazing size fool you. The most incredible thing about CMS is not its size or its weight, but its precision.
After a proton-proton collision inside CMS, we have to know where the produced particles originate from and where they went. We have to do this with a precision of 10 microns. In order to do so, we use a silicon detector which is finely segmented. For example, the inner tracker of CMS, which is behind me, consists of 13 layers of silicon sensors, which are divided into strips and pixels. These strips and pixels are only a few tenths of a micron wide. This is much smaller than the diameter of a human hair. We are placing right now these silicon sensors in the layers with a precision of only 100 micron in this volume of 5 by 2.4 meters.
The detector is made of many concentric layers, a bit like an onion.